Welcome. This video is going to talk a little bit about the development of the periodic table and then look at the organization of it and the terms that we use to describe different features on the table. So in the late 1700s, Antoine Lavoisier made a list of all the elements known at that time, and there were 33 of the 92 natural elements on Earth known at that time. And then John Newland, shortly after that, organized the elements in groups of 7, and he called it the law of octaves, and he thought there was some kind of relationship with like a musical octave. But because that was groups of 7, it didn't work because we found out later that it's really groups of 8. Now, as silly as that sounds, 7 takes you through the representative elements without the noble gases. But once the noble gases come in, now we need an 8th family there. So then the two fellows who are credited with doing most of the work were Luther Meyer and Dmitri Mendeleev, and they each came up with a similar table at the same time, even though one was working in Germany and the other was working in Russia, but their tables were both based on increasing atomic mass and similar chemical properties. So Mendeleev is generally given credit because he published his idea before Meyer, and interesting enough, he actually had his table turned 90 degrees sideways. And at some point along the line, people said, this would make more sense if we turned it the other direction, so they did. Another big improvement to it was several scientists had noticed that in a couple of places, like with nickel and cobalt, you had to flip-flop them in order for nickel and cobalt to be in the family they should be. Anyway, there were a couple of quirks where the atomic mass didn't quite fit where you wanted to flip-flop elements, and Mosley found the solution to this issue by determining that atomic number is the number of protons, and the table should actually be arranged by atomic number, which in most cases is also increasing atomic mass. So the modern table is now arranged by what we call periodic law, which is said to be the increasing atomic number with repeating patterns of physical and chemical properties. So here's a table I'm going to refer back to several times, or you could just flip open your book. The back page has this in it, or you could probably find any table that you want to take a look at, but we'll refer to some of this terminology and explain it a little more. And I want to add a couple things to this table. They've numbered a number of the families, well, 8 of the families, but they skipped these here, and they should have included, let me get my pen here, they should have included this as 3B, 4B, oops, that's on a B. Seven B, 8B, 9B, and then these are all considered 10B. Or you can also number the groups, just go from left to right. From 1 to 18. The other mark they didn't put on here is they didn't let you know the period names, and these just get numbered 1 through 7. This table makes it really clear this is also part of row 6 and row 7. We'll take a look at the first terms here. Groups or families, as I was just showing on the previous table, are the 18 columns on the table, and they can be numbered 1 to 18, or they can be used using the A and B designation, which really the A is letting you know that they're what we call representative elements, and the B's are transition elements. And we'll define the difference in those shortly. And then the 7 rows on the periodic table, as I just numbered, are the what we call the periods, and the 2 extra rows at the very bottom actually belong in rows 6 and 7, as our table shows us. So some other terminology, then the representative and the transition elements, the group A families, or group 1, 2, and 13 to 18, so the outer rows on the left and right side of the table, they are called representative elements, and they have outer electrons that are being put into the s or the p orbital. Whereas transition elements, those inside families from groups 3 to 12, or what we call the B families, those are putting outer electrons into the d orbital, or if it's the 2 rows that get added to, or the 2 groups that get added to rows 6 and 7, they're adding them to the f orbital. And then you might have noticed a zigzag line on the table. All the elements to the left of the zigzag line, except for hydrogen, are metals. And you notice that's most of the elements. In fact, 4 out of 5 elements are metals. And characteristics are metals. I don't think any of these will come as a surprise to you that they're shiny when they're clean. They tend to be solids at room temperature, except for mercury. They're good conductors of heat and electricity. And then they're also what we call malleable, or can be flattened into sheets, and ductile, can be stretched out into wires. A couple of families of metals that get special names are family 1 or 1A is called the alkali metals because they're very reactive. So they're found as compounds or combined with something else in nature and not in pure form. And they tend to form basic solutions when they're dissolved in water. And family 2 or 2A is very similar. They're called alkaline earth metals and are nearly as reactive as group 1A and also form basic solutions. The transition metals, or the B groups, the ones in groups 3 through 12 that are up on top and filling up their d orbital are called transition metals, and then the 2 families down below, the lanthanids and actinids, are actually called intertransition metals, but together they make up what we call the transition elements. And then along the zigzag line are elements that are called metalloids, and that's because they can have properties of both metals and nonmetals. For example, silicon is on the nonmetal side of the line, but it can be an excellent conductor, so that makes it more like a metal. Well, aluminum is along the metalloid line, and it behaves pretty much like a metal all the time and really has little to no nonmetal characteristics. So metalloids have varying levels of characteristics of both metals and nonmetals. And then the far right side of the zigzag are the nonmetals. And these characters are that they're dull quite often. Many are gases at room temperature, and they tend to be poor conductors of heat and electricity. Also, when you hit these with a hammer, you're not going to be able to flatten them into a sheet or draw them out into a wire. They're going to tend to shatter easily, or we describe them as being brittle. And that's a quick introduction to the periodic table.